You ever think about the fizz in your soda? Or the tank on a scuba diver's back? Or, I don't know, the fluid in a hospital IV drip? They seem like they have nothing in common, right? Well, what if I told you they're all governed by the exact same fundamental chemical principles? Today, we are diving deep into the invisible world of solutions, and you're going to see how the drink in your hand is connected to life or death situations.
And this quote right here, it just nails it. Think about it. Pretty much nothing you interact with is a pure substance. The air we breathe, the water in the ocean, even our own blood. It's all a complex jumble of stuff. And that idea, that everything is a mixture, that's where our story begins.
So what is it? What's the hidden link between a can of pop, a deep-sea dive, and a medical treatment? Well, if everything around us is a mixture, then the secret has to be in understanding a very particular kind of mixture. And that is the solution. So, what makes a solution a solution? It's what we call a homogeneous mixture. Now, that's just a fancy, scientific way of saying it's blended perfectly, like completely evenly. You know when you stir salt into water? After a second, you can't see the individual salt grains anymore. Every single drop of that water is now equally salty. That perfect uniform blend, that is the heart of a solution. Okay, first up, the invisible ingredients of life. So, every solution is made of two key players. You've got the solute, which is the thing that gets dissolved, like the sugar in your coffee. And then you have the solvent, which is the thing that does the dissolving. So the coffee itself, solute and solvent. That's it.
Part 2. How strong is it? So, you know how you might say your coffee is strong? Well, in chemistry, strong isn't quite good enough. We need to be way more precise. So, how do chemists actually measure the strength, or what we call the concentration, of a solution? Well, it turns out we have a whole toolkit for that. First tool out of the box is mass percentage. And just like it sounds, it's all about comparing the mass of one part to the mass of the whole thing. This is a huge one in industrial settings, mostly because it's just so simple and reliable.
So, the formula is simple. You take the mass of your key ingredient and divide it by the total mass of the solution. Let's take bleach. When you see 3.62% on the bottle, it just means that in every 100 grams of that liquid, exactly 3.62 grams is the active ingredient, sodium hypochlorite. The other 96-point-something grams, mostly just water.
But hang on, what if you're mixing two liquids? Weighing them can be a pain. It's way easier to just measure their volume. And for that, we pull out our next tool, volume percentage. It's the same basic idea. We're just talking about liters or milliliters instead of grams.
The antifreeze in your car is a perfect example of this. A 35% solution means that for every 100 milliliters of that fluid in your radiator, 35 milliliters are pure ethylene glycol. And that specific ratio is what keeps your engine from freezing up in the winter or overheating in the summer. It's a precisely engineered solution.
Okay, but what about when the amount of something is incredibly small? I mean, seriously tiny, like a single drop of something in an entire swimming pool. For that, percentages are too clunky. We need a much, much finer tool. And that tool is parts per million, or ppm. This is absolutely critical when we're dealing with trace amounts like pollutants in the water supply.
And this is where concentration can be a matter of public health. Take fluoride in our drinking water. At just 1 part per million, that's 1 milligram for every liter of water, it does wonders for preventing tooth decay. But if you bump that concentration up to just 1.5 ppm, it can start to mottle teeth. A little higher, and it becomes toxic. It's the ultimate example of how the dose truly makes the poison.
All right, brace yourselves. We're about to hit two terms that sound so similar they trip up chemistry students everywhere: molarity and molality. Pay close attention here, because the difference is subtle, but it's incredibly important. Molarity, with an R, is moles of the solute per liter of the entire solution. But molality, with an L, is moles of solute per kilogram of just the solvent. See the difference? One's about the whole solution's volume. The other is about the solvent's mass.
And here's why that tiny difference is a huge deal. What happens when you heat up a liquid? Right, it expands. Its volume changes. Well, since molarity is based on volume, that means its value can change just by turning up the heat in the lab. But mass doesn't change with temperature. So molality stays constant.
That makes it the much more stable and reliable measurement for any experiment where the temperature isn't perfectly controlled.
Number 3, the unseen rules of mixing. Okay, so we know how to define a solution and how to measure its strength. But that brings up a more basic question. Why do some things, like sugar, dissolve so easily in water, while other things, like oil, just don't? They refuse to mix. It all boils down to one beautifully simple rule.
And here it is. Like dissolves like. It's one of the most powerful rules of thumb in all of chemistry. All it means is that polar molecules, like water, are really good at dissolving other polar things, like salt. And nonpolar molecules, like oil, are great at dissolving other nonpolar things, like grease. This is the very reason you need soap to wash your hands. Soap acts like a bridge between the nonpolar oil on your skin and the polar water from the tap.
Okay, part 4, pressure, pop, and peril. This is where we bring it all together. We're going to see how these invisible rules of solutions play out in the real world, where they can be the difference between a fizzy drink and a serious medical emergency.
Let's start with something we've all experienced. You crack open a can of soda. You hear that satisfying psh, shh. You see the bubbles rush to the top. But why? What is physically happening in there at the molecular level?
So, inside that sealed can, it's a high-pressure environment. The manufacturer has literally forced a whole bunch of carbon dioxide gas into the liquid. You can think of it like shoving extra people onto an already crowded subway train. The pressure is so high, it forces those CO2 molecules to dissolve into the water, where they stay trapped.
But the second you pop that cab, whoosh, all that pressure is released. And suddenly, there's nothing holding those gas molecules in the liquid anymore. They rush to get out, rapidly escaping the solution. And that rush is what creates all the fizz and bubbles we see. The solution is literally unmixing itself right before our eyes.
And there's a name for this whole phenomenon. It's called Henry's Law. And all it really says is that the amount of gas you can dissolve in a liquid is directly tied to the pressure of that gas above the liquid. It's a simple relationship. More pressure means more gas dissolves. Less pressure, less gas dissolves. It's the law of fizz.
But Henry's Law explains so much more than just soft drinks. For a scuba diver, the intense pressure deep underwater forces extra nitrogen from their air tank to dissolve into their bloodstream. If they surface too quickly, that pressure disappears, and the nitrogen bubbles out of their blood, causing an incredibly painful and dangerous condition called the bends. And the same law works in reverse for a mountain climber. At high altitude, the air pressure is low, so less oxygen can dissolve into their blood. This leads to a dangerous state called anoxia. It is the exact same scientific principle, just with life or death consequences.
So, we've seen how a single, simple law of pressure dictates everything from a soda going flat to a diver's worst nightmare. It's the master key for understanding how gases and liquids mix, but that just opens up another question, doesn't it? What happens when it's not a gas and a liquid, but two liquids trying to mix together? Well, that's a whole different story for another explainer.